Everyone. So we're going to wrap up chapter 13 in Steck, Steck 13.6 on computer memory, and a little bit of discussion on um, a on microprocessor and how they interact with memory. Um, so let's start off with computer memory first. I've been saying over and over these D flip-flops that we've been making in the lab, right? They are essentially computer memory. So these D flip-flops, you can make them out of NAND gates like this, right? 4 NAND gates and an inverter. And then you can have a D flip-flop that gives you, Q and Q bars, depending on what the state of D, the data you're sending in, and whether or not you can write to that is determined by the clock, right? Which pulses up and down. In applications such as the ones in your computer, um, the read and write of the memory is actually in use all the time. So when you have that, basically you need to make sure that the clock is, up all the time. And the way that people do this and save a little bit of power is by basically swapping out the left two NAND gates with OR gates, as you can see here. So that's the difference. What this does to the logic is that instead of the clock being high, you're able to write to the memory. It's actually when the clock is low, you are able to write into the memory. So instead of calling it a clock, it's going to be called not E. And the E stands for enable. Okay. So since this is a low, right, you want it to be 0, right? If not enable is false, that means it is enable. Okay, so just be a little careful of the double negatives there. Um, so be aware of that. And so whenever you read a spec sheet, right, when it's like R bar or S bar, it just means that it's true when it's 0 instead, right? So it's the double not that you're dealing with. Okay. And the rest of the circuits works the same way. You do have to move the NOT gates up to S bar instead of at R bar, but the rest of the circuit stays the same because all the input has to be flipped. Okay, so these D flip flop can be represented by this functional diagram where it's just D, and then E bar here, right, and then the NOT here you can see it, and then Q. Okay, and that's the output for your data. Okay, and you never read the Q bar because you know it's always going to be opposite of Q anyway. Okay, and so an example of this is the simplest example that makes a little bit use of all the technology involved is a 8-bit random access memory module. Okay, so RAM stands for random access memory. That means it allows one to access those particular flip-flops at any time you want, at any interval, at any position you want. So, and the way you do this is basically by putting your D flip-flops all in a row, and then you're going to have a multiplexer and a demultiplexer on both sides. Okay, so that's what the schematic will look like here. Okay, so there's 8 bits, so you have the 8 D flip-flops here. Okay, and what happened is that the data comes in on just a single line. Let's do that in a different color. Green looks good. Okay, the data comes in right here, and it goes to all the D flip-flops, not just one of them. The reason you do that is so that you can actually, these data lines are going to be wires that's coming out of the DRAM, the module, the little gold pins that you see on RAMs. That's what this wire is. Okay, that's the data line. Okay, but why would you want to send all the data to all of them? And that's because you don't. So what you do, or what they do, is that you can actually have an output of a demultiplexer that allows you to select, in this case, up to 8, because we need a 3-bit selector in our demultiplexer. And then this write enable key, well, these write, not write enable key, because of the bar there, allows you to send the output to be not enabled, right? Meaning when it's 0 is enabled, when it's 1 is not enabled. And the selector picks which memory you're actually writing to, okay? Because if it's not enabled, right, then that memory just ignores the data input, okay? And that the information will not be stored or changed. And they say what the computer, what the the hardware, which is actually the chipset on your motherboard, what it does is just cycles through all these memory over and over and over again, and then the data in knows which one you're trying to write to, and therefore it goes to the right slot. You're basically just putting a slot in whichever data bits that you're inputting, and that's how you store things in a computer memory module. Of course, you want to read it out also. Okay, the same, right, selector, ooh, that's a pen instead of highlighter, right, also goes to a multiplexer, right? Multiplexer takes multiple inputs and gives you one, multiple inputs and gives you one output, okay? And what this multiplexer is connected to is the output for all of these. So whenever you select, right, the particular output, let's say I want to read out channel 1, right? Channel 1 is the one that gets sent to the output as opposed to all of them, okay? There's also an extra line here, which is the not read enable, so opposite read enable, right? So this is a little NOT gate here that allows you to basically either block or not block the data that's coming out. That's just a safety issue where when the whatever you connect to this side, maybe a processor, right? If that processor is not ready for you, you don't want to send that information through yet. Okay, that's what this read enable allows you to choose. Okay, so obviously 8 bits is not that much, but this is probably like the minimal size diagram we can put on a piece of paper and then still make sense of it, because once you get to like 64-bit or gigabit, you're just gonna have wires all over the place. So you're not gonna be able to figure out what's going on there. So this is a very good conceptual view of how computer memory are written and read out through these multiplexers on your D flip-flops. Okay, great. More examples. So this 6116 SRAM, the S stands for static. We're gonna see there's a slight difference on what we used and then the ones we just talked about. The static RAM, right? This is a 2 kilobits times 8, right? That means it has 2 kilobytes. So 2 kilobytes is still pretty small. It's like a small, text file. And this has 8, oops, right? An 8-bit selector. So 2 to the 8 gives you this 2048 different ways, different memory address to select from. Okay, and then these are the inputs and outputs. They are shared, so you cannot read and write at the same time, because often you connect them to the same thing anyway. Because let's say, oh, you want to the CPU is the processor wants to read this memory. The same processor might want to request to write to the same memory address also. So the input and outputs are actually going to the same address, and there's 8 of them. Okay, and then the rest are voltages, and then oops, did I not count correctly? Yeah, so this is 10-bit selector. So 2 to the 10 gives you the 2048 bit selection of which address to go to. Okay, and then of course you have the write enable, the read enable. So the O means output, an A10, right? And then you can also force a reset on the chip if you need to clear the memory. Okay, so that's an SRAM module. There are other types of memory. The one that are most common to consumers are DRAMs. They're actually mostly called these days DDRs. So if you buy a DDR4 module, that's what you're buying. Um, so these type of RAM can only hold data for the order of a milliseconds, but the reason is that they are cheap to make. The reason that they can only hold data for a millisecond is that inside these D flip-flops, remember these guys, okay? Inside them, right, they are logic gates. And then inside those logic gates are transistors. Those transistors, right, in order for them to hold a particular 1 or 0, right, they have to have a little bit of capacitor in there in order to store the charge, okay? And for DRAM, the charge on those little capacitors leaks out very quickly. So that means it cannot hold the information for very long. So on the order of a millisecond. Where static RAM, they're designed to have larger capacitance, and therefore, um, even though there's a little bit of leakage current out of the module, what happens is that it can hold that memory for, something order of, days or something like that. Okay. So, but this is the cheapest thing, and they're fast, right? This is why we use them. Um, so I think a lot of memory module probably has like a 4K or 2K refresh. Basically, what that means is that all the information on there has to be refreshed every, 1/4000th of a second, whatever that is. Okay. Otherwise, it just loses that memory. So it's a very, very eternal sunshine of the spotless memory module, let's say. Okay, so there's static RAM, which is what we talk about mostly from up there. They come in little chips like this, so you can mount them on the board with a surface mount. This is another surface mount, but these are various different SRAM chips that you can buy. And these are, and you have these in your computer and your phone also. These tend to store information that you want to change all the time, but right, you don't want to lose it. Let's say like the dates on your computer. When you turn off your computer, somehow the computer remembers what date and time it is, right? So these are actually stored there. So these are things that are changing, but you want to keep it um, um, for a long time. And these, like for example, the clock on these, it uses a little tiny battery, that lasts for 10 years. And then it will just keep it powered. Oh, you can maybe even see the battery here. You can keep it powered, right? And then not. And then remember what date it is when your computer turns on. Okay. Um, Read-only memory. This is stuff that you never want to change because, as the name says, it's read-only. You cannot write to it. So once you install this chip, whatever information on there you got is the information you got. You cannot write to it. There's only read lines. Okay, there's no writing lines. Okay. These are typically hard solder onto your motherboard. You'll see a little square chips like this where it basically tells the computer, oh, this is the path if you want to go to the USB. This is the path if you want to go to the Ethernet. Because these are information that never changes once the motherboard has been designed, so you don't need to change it. And so that's why you put them into read-only memory. So when it's manufactured with those particular instructions already, you cannot change it. Okay. Programmable memory, programmable read-only memory. May kind of sound kind of silly. Like read-only memory means, oh, you cannot write to it. There's some slight modification to that. There are ways to write to these read-only memory, but you can only do it once. The way these are designed, the arrays are designed so that they're not connected at first. But what you do is you program it at one time at a much higher voltage than you would read out of it, and therefore it solidify those connections. When those connections are made once, then you're done. Okay, you can write once and do it done. Okay, and this is actually like very widely used in physics experiments because sometimes a lot of times we want to program something, um, but we don't want to talk to TSMC or a chip manufacturer. Can you make this one chip for us that does this particular routing, right? Because typically they would make this for a motherboard where they will sell, millions of units. But physics experiment, we just need like one or two of them, and you don't want to deal with that. So we tend to use programmable read-only memory, where you have a special circuit that basically writes to these these memory once, and then you move the chip and you put it in what you actually use it for, and then that memory is storing the same information. And this is more for like the DIY version of it, or a physics experiment where you would program the memory once, and then you would never need to change it again. Okay, so one more modification from this is erasable programmable read-only memory. Okay, so maybe sometimes the constant you program into it is not quite constant, or you need to change something. There are ways around it. The way this type of chip works is that what you do is they put a little window there. You can see it here, and that little window is where all the wirings are. The wiring are for the read only for the memory. Okay, and what you do is you shine a UV light on it, and that kind of increase the energy states of all the electrons in there, and then you're able to program it if that UV light is on. If the UV light is off, then there's no programming. Okay, and this is a way to keep things have memory that are less volatile than your DDR RAM, which only keeps the information for a fraction of well, it keeps it for a few milliseconds, but you don't want to count on that. Okay, the last thing we'll talk about is states of machine with memory, and this kind of gives us kind of a big overview of how a computer actually works. So the fundamental principle is that, right, now that we have memory, right, it gives us like, basically infinite computational capabilities. Okay. Okay. And the way you want to um, view, how the process work is that, once again, right, you have some logic gate that can do computation for you, multiply, add, shift, change this vector to that, do it matrix inversion or whatever you want to do. Okay. And then you have memory that stores that information for you, or you can read from it. Okay. So you have an output, right, from these logic gate that can go to the registers. Okay. And then the registers can be read out as inputs also, right? Because maybe you want to read out the previous calculation you did. So you can do it iteratively. And then eventually you have an input and output that controls everything, right? Okay. And this is, of course, the sequential part, which requires this clock to be going up and down to tell the register how to sync up. Okay. So you want to make sure that, the logic gate inputs are getting the most updated data from the register. So when you do the send update, okay, you want the register to you don't want to do things every clock cycle. Let's just say that, okay? Because what happened is that, right, let's say you multiply some numbers together, using your inputs. Let's do a different color then, because I use red already. Use green, right? Let's say you have some inputs, and maybe you're adding, 3 over here in decimal, and then, the number that's stored in your register is 5. So this number turns out to be 8, okay? And you want to send that output to your register, store 8, okay? That doesn't happen in a single clock cycle, because remember that there's a delay, right? So this number 8 is actually, well, it needs 4 bits now, right? It's 4 bits information, right? That may even need, and typically these memory bank would have more than 4 channels. So you can always see that there's one that's 8 up there, right? This information gets stored, but, right, it gets into the memory after one more clock cycle. Okay, so you have the clock cycle that does your computation. You have one clock cycle to store stuff. Okay, and then you have one more clock cycle in order for you to read it. Okay, if you wanted to use it for your next output, and then you have your next clock cycle. So a lot of times what you want to do is actually you want these things to hold and not do anything. So a lot of times, actually about half the time, your processor and your memory are just waiting for one or the other. Okay, this is kind of the inefficiency of these. Okay, so we already kind of looked at the divide by 3 example, right? This hold allows it to basically, you always want to have this ability to hold on to your memory and therefore not change it on the very next clock cycle. So this hold input, right, which is made by just adding a multiplexer to your, in this case, the divide by 3 counter, right, allows you to, well, instead of changing to the next cycle every time, what you want to do is just hold on to it. So what happened is that if the hold is equal to 1, this input just stays as 1. But if hold is 0, then it moves on, it counts up, right? Oh, you want to hold here, then you can just hold 0, 1. And then it keeps going on. Oh, you don't need to hold, then you just keep going, okay? And that's how you want to program these things. And well, this is going to turn into an interesting thing when just holding 1, 1, okay? Or you go nowhere. Just a little bit, I really want you guys to read what Steck wrote. So I'm going to comment my, little picture perspective on it, right? Will be a little bit different. So the textbook is a little bit behind of what people do today. But as we, discussed through the introduction to FPGA, and this is basically an FPGA and a microprocessor, that's how it works. You can program your FPGA into a microprocessor. That's, as we will see in lab 13, which is the last lab. Okay. But so now we have all these logic gates, right? We can do multiplexing. We have memories, right? All these tools combine together to make computational possible, okay? So the difference between our logic gate is that, they are programmable through these instruction sets, right? This is your Verilog code, right? Right, that you're doing. These are instructions that you're sending. That's actually what the bit stream is that you send when you program your device. Okay. So what happened is that, right, you have some logic gate that you that are general use, so you can do whatever you want. This instruction set gets sent into it. Okay, that way it makes the right connection. Basically, you're reprogramming the FPGA. So in a microprocessor, this happens on the orders of nanoseconds as opposed to, 10 seconds or whatever it is through a USB. So you don't want to program your processor through a USB. Okay, so this sets up all these logic gates, makes the connection that you need, right? Let's say you want to add, right? Okay, so it can take inputs, right, from, the external. So if you type in 5, right, then the 5 will go in here. Okay, but it can also take inputs from your memory. So let's say you have 5 coming in here, and then you have 8 coming in here. Like, add those two numbers together. Now the number is 13, and say, oh, the number is 13. That's the answer. Okay, but it can also save that information, right, into your register. And this is where the demultiplexer works, where you have multiple bits coming in here, right? And that demultiplexer sends these information one at a time into the register and record what you just calculated, so you can save that information for your next calculation, for example. So this is usually where we would do more microprocessors, but at this point on, this gives you kind of the idea of what the microprocessor is, and we'll have a lab that does exactly this, where you're feeding input and output, which is going to do a calculator, just adding, a few numbers together and remembering them. But we're going to, kind of skip to, some of the applications of these, and you will not have to program your own microprocessor in the next couple of labs. Not this one. This one you actually do a very simple one, But after that, a little microprocessor that can do like play MP3, or one that can do data acquisition, meaning you can actually read out, any device you want. If you have like a radio signal, you want to figure out what the wavelength is, you can detect that, put it on your data acquisition system, and record it on the computer, and then you can look at it as much as you want. And that way, it interacts through these registers. And one more thing I just want to note is that, yes, these registers are in your electronics hardware. Okay. So this can be, maybe your RAM or something like that, right? A lot of times this needs to get transferred to storage. Okay. And a lot of this storage is going to be through these um, SIPOs, so the serial in, parallel out, or piezo, the parallel in, serial out, so that you can transfer the data over. But hopefully, um, we don't have to talk about the storage side, because basically once you have the data in ones and zero in your register, you can just write those out into a more permanent storage, and so that way you can save it on an SD card or SSD. Okay, so that's all for this lecture, and I will see you guys in class Monday.